All right, I'm going to switch to share my screen rather than that application. There we go. Okay, so the point of this hangout is to try and figure out some things about the stars, specifically their brightness or magnitude, and whether a star like Polaris should be visible from Earth. So I'm kind of new. Like, I didn't really get into astronomy hardcore until August when I was preparing to go see the eclipse. I'd always been interested in astronomy as a kid, and I know I took an astronomy course or two in college. But since a couple of years ago when I got a telescope, I've actually really been interested in looking at the night sky, looking at the sun through a filter and whatnot. So now I'm interested in the brightness of stars. So for some basic terminology, we know the unit of distance called a light year. It's the distance that light travels in a vacuum in 1 year. There's a unit of distance called a parsec, and a parsec is about 3.2616 light years. And the parsec will come into play when we talk about magnitude. Are my audio levels decent?
I'm not listening to the live stream, but I'll go ahead and do that.
Oh yeah, I should do that too, just to make sure that's working.
Yeah, your audio is fine.
Okay, cool. Thank you. We also have the unit of distance called the astronomical unit, or the AU, and that's about 93 million miles. And that's the distance from the Earth to the Sun. It's not always 93 million miles, but I believe the AU is like the average distance from the Earth to the Sun. Light year is 63,239 astronomical units. When we're dealing with the brightness of stars, in astronomy, we have a brightness scale called magnitude. The magnitude scale is logarithmic in nature. Every 5 points of magnitude equals 100 times change in brightness. And the lower the magnitude is, the brighter the star is. So for example, a star with a magnitude of -2 is 100 times brighter than a star with magnitude 3, because the difference between -2 and 3 is 5. And every 5 points of magnitude is 100 times of brightness. There are two types of magnitude when dealing with stars. There's apparent magnitude and absolute magnitude. Apparent is how bright a star looks like from Earth, and absolute magnitude is a way of standardizing a star's magnitude by assuming a constant distance. So a star's absolute magnitude is its brightness when observed from a distance of 10 parsecs, or about 32.6 light years away. So that way, if you know two stars' absolute magnitudes, you can know definitively which is brighter than the other, because their absolute magnitude deals with a constant distance from you. So if star A has a magnitude of 5 and star B has a magnitude of 6, and this is their absolute magnitude, you know that star A is brighter than star B, because star A appears brighter at the same distance from you than star B. Make sense so far? I hope so. We also know about the inverse square law of brightness. This has to do with the change in brightness over distance. And the law states that the perceived brightness of an object is inversely proportional to the square of the distance from the source. So if an object has a perceived brightness of 1 at a distance of 1 unit, it will appear 1/4 times as bright from a distance of 2 units, and 1/9 times as bright at a distance of 3 units. We can use the law of inverse square of brightness in conjunction with astronomical magnitude. If a star has a perceived brightness of B, and this is brightness, not magnitude, but if the star has a perceived brightness of B at a distance of 1 unit, then it will have a perceived brightness of B over 100 at a distance of 10 units. And we know that a change in 100 times the brightness is a change in 5 points of apparent magnitude. So if that same star has an apparent magnitude of m at a distance of 1 unit, it will have an apparent magnitude of m plus 5 at a distance of 10 units. So that's a way that we can use the inverse square law of brightness in conjunction with the with magnitude. If we know the actual distances, then we can know how much more or how much less bright an object will appear, both in terms of its actual brightness and in terms of its apparent magnitude. So now looking at Polaris and the sun, these values, I will admit right now, I got them from Wikipedia. I got them from the sidebar of Wikipedia, and the sidebar of Wikipedia for the Polaris page and for the sun page. The footnotes or the side notes all indicate that they're getting these from standard astronomical tables. So I'm assuming that Wikipedia is giving me accurate information for these.
If I can interrupt for just a second, Jeffrey, Astronomy Live has just joined the Hangout.
Thank you, Astronomy Live. I'm talking about stars and their magnitude and their distances, and trying to determine if I can provide a sound reason to believe that Polaris, as far away as it is, should still be visible from Earth. Because there's somebody I've been talking to on YouTube who says that a star 433.8 light years away shouldn't be visible from Earth. And I'm trying to demonstrate that it could be visible if it's big enough and bright enough, using what we know about Polaris and the sun and their magnitudes and whatnot.
Gotcha.
So if at some point I make a blatant mistake or something, or, if there's ever a point where you feel like you can add something, please do interrupt me. I'm not trying to actually make this a lecture, but I'm just trying to go over the notes that I've written and the math that I've done so far.
Okay. Yeah, go ahead.
Okay, thank you. So Polaris's apparent magnitude from Earth is 1.98, and the sun's apparent magnitude is negative 26.74. So if we do the math, that means from the Earth, the sun appears over 307 billion times brighter than Polaris. And my math for that is I find the difference between the 2 points of magnitude. So there's 28.72 points of magnitude difference between the two. I know that every 5 points of magnitude is 100 times the change in brightness. So I could write 28.72 as 25 plus 3.72. Dealing with the factors of 5, I have 100 to the 5th power because I have 5 5s, and that gives me 10 billion. And then the other 3.72 represents 30.76. And the way that I'm doing this is it's basically 100 to the 5th root of 100. So 100 to the 0.2 power. And then if I raise that to 3.72, you get 30.76. That's the math that I've seen that you use to do these magnitude conversions. So 10 billion times. So 10 billion times 30.76 gives me 307.6 billion. So the sun appears 307.6 billion times brighter than Polaris from Earth. But we're really close to the sun, and we're really far away from Polaris. So we should also consider their absolute magnitudes. How bright would they each appear to us if we were 10 parsecs away from them? And the standard chart says that Polaris's absolute magnitude is about negative 3.6. And the sun's absolute magnitude is 4.83. Doing the same kind of math, see that Polaris is about 2,355 times brighter than the sun if they were both viewed from the same distance. Again, I do the math pretty much the same way. I find out the difference between those two magnitudes, and I convert those to I use every 5 equals 100 times, and I get this value of 100 times 23.55, or 2,355 times brighter. Distances. We know that the sun is 1 astronomical unit from the Earth, and Polaris is believed to be about 433.8 light years from Earth. We can do some quick conversions, and we get that Polaris is 27.4 million astronomical units away, so Polaris is 24.3 million times farther from the Earth than the sun is. We can also describe Polaris's distance in terms of parsecs. 3.2616 light years per parsec. So 433.8 light years is about 133 parsecs. Now we consider the brightness compared with distance. And this is kind of my mechanism to make sure that the inverse square law of brightness corresponds in reality to these two differences of magnitude, the apparent versus the absolute. So my reasoning is as follows. If Polaris has an absolute magnitude at 10 parsecs of -3.6, Polaris is actually 133 parsecs away, and we're dealing with a distance factor of 13.3. Polaris is 13.3 times farther away from us than the absolute magnitude would imply. Because it's 13.3 times farther away, we have to reduce its brightness by 1 over 13.3 squared, which is 1 over 176.89. Now, using the defined values of its magnitude, -3.6 versus 1.98. Oh no, that's how I check it. So I compute the magnitude difference using these values here. In other words, what magnitude difference do I need to use to get a difference of 1 over 176.89? And the way I do that, hang on. Yeah, see, now I'm not sure if I did this right. What is 1 over 176.89? What is that number? I'm sorry, bear with me.
You squared the 13.3.
Okay, right. So 1 over 13.3 squared
equals 1 over 67 or 176.89.
Okay. So how do I determine the magnitude difference? Oh, okay. I figured it out now. Okay. So 176.89 is my target number. I showed before that a change in 100 times brightness is a change in 5 points of magnitude. So dealing with the denominator of this fraction, dealing with 176.89, how do I get the number 176.89? How do I get that as in terms of magnitude change? And the answer to that is with this number. So for example, if I were to take 100 to the 0.2 power, if I were to take the fifth root of 100 and raise it to that number, I get 176.888. So 176.89 essentially. And so what this actually means is that this number should be negative because I'm dealing with 1 over 176.89. So the magnitude difference is a negative number here. So I should rewrite my math check as 1.98 plus negative 5.61925. And that should give me a number near 3.6. So let me do this math real quick. It gives me negative 3.639. Negative 3.639. That is very close to negative 3.6. Okay. Okay, so again, to summarize what I did is using Polaris's absolute magnitude and its actual distance, I computed how much dimmer Polaris should appear in terms of brightness, and then represented that change in brightness in terms of magnitude. And the math checks out. I do the same thing for the sun, except instead of the sun being farther away than 10 parsecs, the sun is a whole lot closer than 10 parsecs. So it works out pretty much the same way. I get a magnitude difference between its absolute magnitude and its apparent magnitude from Earth. And okay, so this number is actually 30.5716. No, 31.5716. And when I do a math check with the actual magnitudes of 4.83 and negative 26.74, I again get super, super close. Okay, so that's all the math that I've worked out. And now I'm at the point where I'm trying to say, how can I deduce logically that a star with Polaris's absolute magnitude at a distance, well, I kind of guess I did that. I've shown that Polaris, I've taken Polaris's absolute magnitude and I've adjusted it for the distance it really is. And that gives me the apparent magnitude of essentially 1.98. And so I guess the question that is left is a star with a magnitude of 1.98 visible from Earth? And we know that to be true because there are other things in the sky that are dimmer than that magnitude, and we can see them. My only qualm here is that my proof of this, or my argument, seems to be kind of circular because I'm using the defined values of the magnitude of Polaris and the magnitude of the sun. And these are not values I've computed. These are values that other scientists have computed and which are generally accepted in the scientific community. I guess what I've done is simply mathematically show that if Polaris has the absolute magnitude that the scientists say it has, and if Polaris is as far away from the Earth as the scientists say it is, then its apparent magnitude from Earth, which I've computed, matches the apparent magnitude from Earth that the scientists say that it has. And the apparent magnitude of nearly 2 is something that's visible from the face of the Earth under the right conditions. So I don't know, that satisfies me. I don't think it will satisfy INREM, who is the person I'm doing this for, because I'm pretty sure the issue with him is he's not sure why we should believe that something that's 430 light years away should be visible at all. And I guess my argument would simply be, it doesn't matter how far away it is, if it is actually bright enough that the light can travel the distance between us and still be received by our eyes, then yes, the star should be visible. It's really difficult to model this sort of thing in real life, because you would want to be able to do experiments in like a completely dark room, like with super light absorbing walls. You'd want it to be completely dark, and you'd want light sources that you could control their distance and that you could control their brightness. And even then, I don't know how to compute. I don't know how to calculate a light source's magnitude. Like, I don't know how to come up with that number on my own. And I don't know, for example, if there's a way of converting luminosity or like wattage output. I don't know if there's a way of converting that to magnitude. But I guess unless anybody has anything to contribute here, I'm satisfied that my math was correct.
Oh, sorry, I was heavily distracted through that, trying to pay attention, but had something else to attend to at the moment. I very much apologize for that. I kind of caught half of what you were saying there towards the end. I did some spot checking here and there, and it looked okay. The math looked fine. Are you trying to? So you want to know, is there a way to convert from something like lumens to magnitude or something? Is that what you need?
Yes, that was that last question, which I was going to get your attention if you weren't already quick to jump on it, astronomy.
Yeah, I was just going to say, like, if there was a way for me to do an experiment where I'm using lights or lasers to represent stars, like, how would I convert lumens to, how would I determine magnitude from lumens?
Right. So I actually have a spreadsheet handy that I developed some time ago, and I can't remember why or when, but it converts from magnitude. If you put in the lumens, then it gives you the distance. So it works the other way around, sort of. So I guess it would make sense for what you're doing. You kind of what you're trying to get
out there. I'm sorry.
Okay, so I'm sorry. You were saying, so you want the formula to convert from magnitude to lumens, which depends on distance. I mean, I'm talking apparent magnitude here. Excuse me. Sorry, I'm talking apparent magnitude here, although you could do it with absolute magnitude just by assuming the 10 parsec distance. But okay, so let's see here. What is the apparent magnitude? I need to pull that up. What is the apparent magnitude of Polaris? Magnitude Polaris. Let me just make sure the spreadsheet works. It's been a long time since I've used it, that's for sure. So it's 1.97, is that right? Apparent magnitude Polaris. That sounds about right. And it's stated absolute magnitude. Come on. Oh my goodness. I can't get this board to work. Is what? It says that's 1.97. Okay, they can't both be right. Apparent magnitude 1.98 apparent magnitude. What is the absolute magnitude? Negative 3.6?
I thought it was negative 3.6.
Okay. Let's see here. 1.97. Okay, this spreadsheet's totally doing it the opposite way from what I actually need. What I really need is to calculate magnitude, or lumens based on magnitude and distance instead of distance based on magnitude and lumens, which looks like it's a pretty simple conversion here. Yeah, let me just do this the right way. I need a piece of paper. I have it in the spreadsheet, but sometimes it's easier to visualize this with proper math notation instead of trying to interpret spreadsheet language.
Yeah.
So candela, square root of candela over, what is that? Lux. Okay. And then that whole deal is divided by 1,000. So if my spreadsheet's right, that is distance. But we want to solve the opposite. We want to solve the lumens. And candela's directly proportional to lumens. Lux is proportional to magnitude. Okay. So we want to solve for candela, basically. Okay, so that's easy enough. And Lux. So Lux will be equal to, if my math is right, Lux will be equal to candelas divided by distance times 1,000 squared. I'm sure that 1,000 factor, that's just got to be converting from meters to kilometers or something like that. Yeah, that's what it is, actually. It's converting to kilometers in the spreadsheet. Sorry. Got my paper. But that's all that is. Okay, that makes some sense. So, and then magnitude. Okay, so Lux is equal to 10 to the power of negative 14.18 minus the magnitude divided by 2.5, according to my spreadsheet.
Can you read that off one more time?
Lux, according to my spreadsheet here, if this spreadsheet's right, I'm assuming it is equal, here, I'll just paste it in the group chat, actually. That'd probably be easiest.
Yeah.
Keyboard to work. Here's the group chat. Here's the group chat. Okay. So I just pasted the formula there in the group chat within the Hangout here, so you can see that formula. That's what Lux is equal to in the equation. So you can pull magnitude out of that, if you see what I'm saying.
Yeah, good old math. All right.
And then that whole deal is equal to candelas. Candelas are equal to lumens divided here. I'll post this formula too. So candelas equals this. This is all math I haven't had to do in a long time.
Math I've never done before.
C3 is lumens. Okay, so that's equal to lumens. This is all sort of in Excel language here. Candelas equals lumens divided by 4 times pi in parentheses. And then distance. But we're solving for Lux. Right. So Lux is equal to, did I give you the formula for Lux yet? Lux is equal to candelas divided by distance. And that's going to be in meters, the distance squared. And you can multiply that times 1,000 for kilometers, right? So there's lux equals candelas divided by distance squared.
Was the top equation, the top one, is that lux or lumens?
That is for lux. That is what lux actually is. Lux is that formula. Okay. So that's from that formula. As you can see, magnitude is part of that. So lux is really just a function of magnitude.
Okay.
Candelas is a function of lumens. And yeah, lux, you can solve for lux if you know the candelas and the distance.
Okay.
So candelas, wait a minute. I might have done something wrong there. No, yeah, no. Is that right? Candelas is equal to lumens. Yeah, candela is a function of lumens, and that's what you're trying to say. Okay. Sorry, which one is it you're solving for? You're solving for lumens, right? Okay, I arranged my equation wrong because you're trying to solve for solve for lumens instead of distance, right? Or is it lux that you want? I'm sorry, it's been a long day. Which one is it you want? You're trying to solve for...
Presumably, I would know the lumens of my light source, and I would know how far away from me it is. So I would use those two starting values and eventually figure out the magnitude.
Magnitude. Okay, so you're trying to solve for magnitude. Right. So I had it the right way around because you're basically trying to solve for lux, which is a function of magnitude.
Okay.
So that's easy enough. That's just... you just basically substitute the candelas formula into where it has candelas there. We're solving for lux, and lux is a function of magnitude. You could rearrange the equation
of both sides,
right? Exactly.
And do a little bit of math to figure out magnitude. Okay.
Yeah, exactly. So you're just trying to pull magnitude out of that equation and solve for that. So it's not that hard.
Okay, cool. I'll do some math with just like, I don't know, like light bulbs up in my ceiling right here and see if I can work out some numbers that sound appropriate. And I found a table on Wikipedia that shows the sun and how many lumens it's said to put out. So I'll see if I can get the sun's amount of lumens and its distance to work out to the proper magnitude. And if it does, then that kind of confirms the equations you've given me and the numbers I have.
Right. So do you have that number off the top? Right. Actually.
Yes.
What is the sun in lumens?
The sun is 3.6 times 10 to the 28 lumens.
10 to the 28th lumens. Okay. Currently failing at typing. 3.6 times 10 to the 28. Okay, and let's see. Polaris is supposed to be how many times the sun's luminosity? 1,260, is that right?
Hang on.
Is that the number you had? I don't know. I'm just pulling this off Wikipedia real quick here.
Yeah, Polaris's luminosity is 1,260 times the luminosity of the sun.
Okay, that's the number I had. All right. So if we plug that in, let's make sure this all makes sense. Yeah, I think that. Yeah, that all makes sense, actually. Okay, so if I plug 3.6 times 10 to the 28 into my spreadsheet, I wonder if I can share this. Yeah, it doesn't show my name. Okay, I know Excel sometimes shows my name at the top, so I have to be cautious about sharing that screen if I have Excel, but actually I have LibreOffice open right now. So here's the spreadsheet that I have. If I plug in 3.6 times 10 to the 28th lumens times 1,260, because it's 1,260 times the sun's luminosity. And we plug in a magnitude here of an apparent magnitude of 1.97. The implied distance is 3.22 times 10 to the 15th kilometers. And if you do the math on that, that works out to 341 light years. So I think that all adds up.
Yeah, 340 light years. Okay. Long live math.
Yeah.
All right. Thank you, Astronomy Live, for your equations.
No problem.
I will definitely use them in whatever future experiments I do. And thank you to Sean and Jared for listening to me read off a Word document that I prepared over the last hour or so.
Hey, I like learning new stuff.
Yeah,
and
it's fun for me too. I hadn't really thought about star magnitude and everything until, you know, this guy asked, well, why can we see Polaris? So
well, that's why I asked Astronomy Live here, because, you know, you asked who all want to join this hangout, and of course, you know, since I promoted it on my channel, I like what you do. I like your intelligence. So yeah, I want to be a part of it. But as soon as I seen what you're doing on screen, I was like, okay, this is something I've never dealt with, so I don't know the equations. Let me see if I can get a hold of somebody who does.
Yeah.
Yeah, so, it's been a long time since I pulled those equations out, so apologies that I had to clean the cobwebs out of my ears, but I think we got there.
That's fine. Thank you so much for that. I will definitely save this.
Yeah, no problem.
All righty. And thank you also to the viewers. I have not been looking at the Hangout chat. I've not been looking at the YouTube chat at all.
You're not missing anything.
Yeah, you haven't missed anything.
I bet you my whiskey eye is more accurate than your eyeball. Okay, with that, we will end the Hangout. Thank you all for participating. Have a good night, and you will see another video from me soon. Bye-bye.